So yes, my name is Uche Onyekpe, and I'll be talking about the application of machine learning to the positioning of autonomous vehicles in GNSS deprived environment. One of the safety critical areas of autonomous vehicle operation is in the navigation. You have that sensors such as the GPS is very useful, for localizing the vehicle to a road, whilst other sensors such as camera, LiDAR, radar, and high definition maps are useful for achieving lane localization of the vehicle. However, there are a couple of issues that affect the navigation sensors present on the autonomous vehicle. With cameras, you have that external light intensity and reflective objects rather within the scenes of the camera affect the operation of the camera. We have that low-cost lidars experience issues when there are heavy fogs, snows, sleets, or rains. And high accurate lidars are very expensive and could easily become theft attractive items and also add thousands to the cost of an autonomous vehicle. And with high definition map, temporal changes to the environment of the road could render it temporarily outdated. On the next slide here, I have an example of a camera failure from 2018 on a Tesla vehicle, where there was a bright intensity from the sun, during the sunrise, and that affected the operation of the camera and led the car to run into the barrier on the middle of the road, as you can see. Despite these challenges, it's quite common for vehicles to still press on using for autonomous vehicle manufacturers to keep on pressing, with using these sensors, and there's quite a lot of research being put into how to address some of these issues at the moment. Looking at the GPS, a GPS is useful for achieving road localization, but it operates based on the principle of triangulation, and it requires at least 3 satellite signals, to perform this triangulation. For a GPS to perform well, there needs to be a direct line of sight between the GPS transmitter and the receiver. But from time to time in certain environments, there is a blockage of this line of sight, and that leads to inaccurate performances. Such environments could be around tall buildings in metropolitan cities, dense tree canopies under the bridges, in tunnels, and a host of others. Tesla, for instance, which has its autopilot vehicle out, relies on a camera to perform localization when there is a short-term absence of this GPS signal. A very common approach to this problem is the use of an inertial navigation system. An inertial navigation system consists of an accelerometer, which is used to measure the acceleration of the vehicle, and the gyroscope, which measures the orientation of the vehicle, given the yaw, pitch, and roll measurements. The beauty of the inertial navigation system compared to several other approaches, such as the camera, is that it does not need to interact with the external environment, to perform localization, and is thus unique compared to these other sensors. Similar to the other sensors, the inertial navigation system has its own peculiar issues. The measurements from the inertial navigation system are plagued by errors, which drift exponentially over time when they are integrated from acceleration to velocity to displacement. And as such, as they are accumulative over time, this leads to a poor navigation solution. What we also have is that due to this error, that is created during the operation of the inertial navigation system, it's quite common for the GPS to be combined with the INS to form a mutually symbiotic relationship where the GPS is continuously used to calibrate the inertial navigation system over time. And when the GPS signal is lost, the inertial navigation system can step in to provide positioning information. However, this process is not as accurate as we'd like it to be, especially for safety critical application as the navigation of autonomous vehicles. What I have on the screen here in terms of the images are an example of this error projection over time. Over a 10-second period, you can see on the graph here that using a physics model to determine the position of the vehicle using an accelerometer of the inertial navigation system, the position of the vehicle achieves an error of about a bit over 18 meters over 10 seconds, which is quite a lot for a 10-second drive. But when you use the machine learning algorithm to integrate the INS and GPS, to better calibrate the INS GPS and combined model, the performance of the INS GPS improves, and we're able to improve the position estimation after 10 seconds, giving a result of about 10 meters, a position error of about 10 meters eventually. Another sensor that has been least explored is the wheel encoder. The wheel encoder is able to measure the speed of the wheels of the vehicle, and this sensor is already present in the vehicle. The beauty of the wheel encoder is that, similar to the inertial navigation sensor, the accelerometer particularly, it doesn't need to interact with its external environment to perform localization. But compared to the accelerometer of the INS, the wheel encoder has less noise and has just one integration step, going from the linear velocity of the vehicle to the position of the vehicle. As such, there is a potential for the wheel encoder to provide better estimation compared to the inertial navigation sensor. Similar to the others, the wheel encoder has its own peculiarities as well, particularly with the state of the vehicle at the point of navigation. We have that, for instance, when there is a change to the state of the driving surface, when it is wet or perhaps on muddy roads, the wheels of the vehicle could slip, and that leads to a wrong information on the speed of the wheel at that particular instance. The state of the tires as well affect the estimation of the right estimation of the vehicle's position at that particular instance, such as the worn out state of the tires. If you create a physics model based on a certain state of the tire, over time it wears out, and the the model becomes incorrect, given that the state of the tires has changed. But similarly, you have changes to the diameter of the tire as well. When you have a large tire diameter compared to the diameter of the tire that was used to create the model, there leads to an overestimation of the vehicle's displacement, and similarly, vice versa, a small tire diameter leads to an underestimation of the vehicle's displacement. It's quite common, for this models to be static. They make use of the state of the vehicle at that particular point of time of modeling, and when this state changes over time, the models are unable to adapt to the change in the characteristics of the vehicle. So the main question, we set out to address is, seeing that wheel encoders are better than, the accelerometers of the inertial navigation system, can we use machine learning to learn these uncertainties that affect the performance of the wheel encoder? But to do that, we came up with, decided to create a physics model that we can use as a baseline to measure the performance of the machine learning-based model. With the physics model, we basically record the speed of the wheel from the wheel encoders for the rear left wheel and the rear right wheel. These measurements contain the uncertainties from the state of the vehicle at the point of measurement. And we're able to get the average of this to wheel speed measurements to determine the speed of the wheel speed measurement of the rear axle. Based on this, using a mapping constant, a fixed mapping constant, we are able to map the speed of the rear axle to the linear velocity of the vehicle. And then using an integration, we're able to convert this linear velocity of the vehicle to the displacement of the vehicle at a particular time duration, which we define as 1 second during the study. So yeah, the displacement of the vehicle using the wheel encoder measurement is what we refer to as X superscript B subscript WHR here, and then by comparing that to the displacement estimation from the GPS signal, we're able to determine the error, the position error from the wheel encoder measurements at that point in time. Then we set out to create a machine learning model based on the recurrent neural network. We implemented a recurrent mechanism in the input layer of the neural network, but also leveraged the recurrent mechanism within the hidden layer of the recurrent neural network. The input to our model is the speed of the 4 wheels of the vehicle. Both the 2 wheels at the front of the vehicle and the 2 wheels at the rear of the vehicle. And we tasked the machine learning model with learning the positioning error of the vehicle at every second. And what we also have here is the optimal parameters we found that were able to give the best performance of the machine learning model. Furthermore, we made use of a Ford Fiesta to collect data across several cities in the UK, making use of sensors already existing in the vehicle. We thought that this was particularly important in order to prevent an increase in the cost of the vehicle by purchasing extra sensors. And we placed a GPS receiver on the top of the vehicle as well for better visibility. Based on this, we conducted 2 studies. The first study was around what we deemed challenging driving scenarios. We sought out to look for scenarios that we thought would be challenging to the vehicle, particularly to the sensors that we had in the vehicle. And these scenarios we noted down to be the roundabout, motorway, hard brakes, so we continuously, slammed the brake on the vehicle to see if the model will be able to pick, spikes in the signals. We tried it on the wet roads as well, particularly for to see if the model was able to pick up slippages of the wheels and learn when the model is slipping and when it isn't, and when the tires rather are slipping and when it isn't. And we also conducted a study on a scenario consisting of successive left and right turns and sharp cornering. And this is particularly depicted in the image you can see on the screen. And lastly, we studied the performance of the model in a scenario with quick changes in the acceleration of the vehicle. In order to evaluate the performance of the model, we made use of a metric which we called CRSE, cumulative root squared error. Seeing that positioning over a period of time is usually cumulative. We particularly took this into consideration, and we used the root squared error metric as well to account for negative predictions and ensure that we are truly able to assess the performance of the models investigated. What I've also done here is to make a comparison to the accelerometer as well. And as you can see from this very first graph here, you can see that the physics model of the accelerometer, drifts exponentially wider, and the error at the end of this 10-second simulated GNSS signal outage window is about 85 to 90 meters. It is quite significant. And as you can see on the blue line there, the application of machine learning to this model is able to improve the performance over time. And but the machine learning approach to the accelerometer provides just about similar results to the physics model of the wheel encoder. But the model that performs the best here is the machine learning model applied to the wheel encoder, which we call WhoNet. And this model, in this particular scenario, produced a result that is as close to 0 as possible. I believe it was about 30 centimeters in this instance. Across the other scenarios as well, we have a figure here illustrating the performance of all the 4 models compared. And across, you can see that the applied WhoNet model, which is the machine learning applied to the wheel encoder data, performs the best of all of them, with the physics model of the accelerometer performing the worst. So this sort of proved to us that the wheel encoder indeed, performs better than the accelerometer, and in this challenging scenarios, the machine learning approach is able to learn the uncertainties within the wheel encoder measurements to improve the position estimation of the vehicle during simulated GPS signal outage. We then decided to conduct a further study in a longer-term GNSS outage. In this case, GNSS is a generic name for global navigation satellite systems. And for this particular study, we made use of GPS specifically. We defined a long-term GNSS outage as 180 seconds. And what we decided to do was, to investigate the performance of this model in several 180-second segments over a total distance of 477 kilometers. And we ensured that the trajectory was characterized by a mixture of several complex scenarios, as we mentioned in the previous slides. The results we achieved from this show that the WhoNet approach was able to perform even better on the longer term GNSS outage scenario. Here we have that with the physics model. This is a sample scenario here, and with the physics model, the error is about 55 meters just after 180 seconds of travel here. Whereas when we implement a machine learning model to learn the uncertainties within the measurements from the WhoNet encoder, we're able to drastically reduce this error to as little as roughly 5 meters. What we also have as well is several other 180-second segments, and it becomes obvious that the machine learning is able to consistently improve the position estimation over all the segments. And the largest distance traveled in any 180-second segment was 5.62 kilometers. And we discovered that the accuracy of the model within this segment was about 8 meters, which is really impressive, and shows that machine learning is able to accurately to a certain degree improve the positioning estimation of vehicles during the absence of GPS signals. But obviously, the next task will be to look for other interesting techniques, be it with machine learning or perhaps with data preprocessing, to help improve the performance further and drive the error as close to zero as possible, especially as the application under consideration is highly safety critical. Thank you very much.